Hi, my name is Ayan, and today I'm going to talk about Gauss's law. Not what you have learned in college. I'm going to talk about Gauss's law in 2D. You may be wondering what is this all about. Let me explain you. So we all know that Gauss's law says that the total electric flux through a closed surface is equal to the total charge inside that surface divided by permittivity. The total flux is independent of the position of the charge, as well it is independent of the shape of the surface. Now let's imagine we live in a two-dimensional world. Well, whether Gauss's law will still be valid, let's explore that scenario. So in 2D world, the closed surface is replaced by a closed curve. Suppose I have a closed curve and I have a charge inside it. How do I take the integral? How do I take the surface integral? There's no surface integral. The surface integral is replaced by boundary integral, where we take a small element on the curve and we make a dot product with the electric field, and then finally we integrate over the entire curve. Something similar to this we are doing, and we expect that this value should be equal to q divided by epsilon naught. Whether this is true or not, let's test it using a simple circle. So if our loop is a simple circle and we have a point charge, our entire calculations becomes very easy. This entire integration over the loop is simply multiplication of electric field with the circumference, because the electric field is same everywhere and it is outward normal at every point. And when we do that, we see that the flux is not constant. The flux is actually dependent on the radius. So Gauss's law is not valid. But wait a minute, don't worry, wait a minute. We can modify Coulomb's law. I told you that we live in a 2D world. I didn't say that in 2D world Coulomb's law will be same. Coulomb's law may be different. So I use a new formula for Coulomb's law, which is where electric field is changing with respect proportional to 1 by r, not 1 by r square. So and the constant is not 1 by 4 pi epsilon naught, it's 1 by 2 pi epsilon naught. So when I do that using the same logic, now I get that the total flux is equal to q by epsilon naught. So this is my claim. If I use this formula as Coulomb's law, this for 2D world, Gauss's law will be valid there. I'm going to show you that this is indeed true using some Python code. Let's jump into that. So this is the Python code that I have written. I'm not going to explain everything, but I want to highlight this line. Here I'm calculating the magnitude of the electric field. First I get whether it's positive or negative, then I multiply by 10,000. I'm taking q as 10,000. This represents 1 by 2 pi. Epsilon naught I'm taking as 1, and finally I am dividing by radius, 1 by r. Let me run this code. So I have a closed loop. My code calculates the flux through each line and finally adds them up. As we do not have any electric field, all the fluxes are 0. Watch what happens when I bring a positive charge. Now the total flux is almost equal to 10,000. Theoretically it should be 10,000, but there are some rounding errors whenever we will work with computers. As I move the positive charge inside the curve, the individual fluxes through each line changes, but the total flux is constant. You can see. The moment I bring a negative charge, the total flux is 0 now. Isn't this amazing? And it doesn't matter where I move these charges, the total flux is almost 0. Watch how smoothly the fluxes through each individual line changes. I can change the shape of this curve when I take a node and I drag it. It affects the adjacent lines, and the flux through them changes, but the total flux doesn't change. I can make the shape anything, but as long as the charge is inside it, the total flux is 10,000. Now slowly I bring it, and now the curve is outside, the positive charge. Now the total flux is almost zero, right? So isn't this amazing? Isn't this amazing? It seems like Gauss law is valid in 2D also, using a little bit of change in the electric field formula. Now I'm going to show you a proof using symmetry. A 2D world can be extended into 3D by dragging everything in the z direction, right? If we use this logic, then my point charge becomes a uniformly charged straight line. Okay? Now we can actually find in physics textbooks that the electric field formula for a uniformly charged straight line is given by this one, which I was using. Well, there are other proofs, but I'm leaving this up to you. And if you can work it out, and if you can find some other ways, other interesting proofs, then please share with me. I hope this video was interesting, and thank you for watching.